Okay.
Except we're going to hit some very important ideas. Thermodynamics is the relation between heat and work. Heat flows from high temperature to low temperature until thermal equilibrium. And first law of thermodynamics, heat flowing can do two things: increase the thermal energy or the internal energy U, and or do work. And there it is in equation form. Quantity of heat, and that can flow in or out. The internal energy can go up or down, and the work can be positive or negative. Okay? Work is force times displacement, so work is power times the change in volume.
Pressure, right?
Thank you, power, pressure. Yeah, and that's what we did over here.
Yeah.
On a PV diagram, the area under the curve equals the work.
That makes sense.
All right?
I feel like there was a question.
How
on this
much
one,
pressure and how much the volume changed.
Mm-hmm.
And question is, what should the pressure be? And I believe this is whatever your starting point is.
Yeah.
Or you have to have a reference point.
Yeah.
I don't believe, although I better be careful here.
Oh, that little triple point thing looks familiar too.
Yeah, that's chemistry. Convection, first law of thermodynamics. Yeah, it's from one pressure to the other.
Again, a final minus initial there.
Yeah. All right, so PV diagrams are what we're going to be playing with today. Okay, state one was in the ice water.
Mm-hmm.
So let's see, this is ice, and we've got the volume, the pressure, and I also added the temperature.
Mm-hmm.
Okay, place syringe and leaving a piston free to move. We've done that. State of the system of the gases. Describe the Q and W. What's the temperature of the water? So we've got hot water.
Yep.
Okay, and so between here, we've got Qn and delta U, the internal energy is proportional to the temperature. So the delta U is positive,
Mm-hmm.
and there's positive work done.
Mm-hmm.
Why? We expanded. So, what's the temperature of the water? We got that. And so, see, basically, this was the same lab that I did with you.
Yeah.
Okay, describe, what about the surroundings? Well, the surroundings would be the water bath.
Mm-hmm.
For the water bath, heat flowed out of the water.
It's opposite there.
The thermal energy of the water went down, and you noticed this when you asked that question about what is the temperature of the water going to change. And then the negative work was done on the atmosphere by the piston.
Mm-hmm. Okay, that makes sense.
Okay, state two, record the volume of air inside the syringe now. We've got that. Now put the syringe back in the water while holding the piston so it can't move. So this
And it's nice.
okay, so we hold the piston here so it can't move.
Mm-hmm.
All right. So describe Q, delta U, and water for the system. So we're back in the ice, yeah?
Mm-hmm.
So now,
We've got it
from here to here,
going out.
Q is out.
Mm-hmm.
And we're going from 52 to 0, so the internal energy is going down.
Decrease.
Got negative internal energy, but no work.
Mm-hmm. Yeah.
Because the volume stayed the same.
Mm-hmm.
And the pressure, although the pressure changed, if the volume changes 0, 0 times anything is 0.
Yeah, okay.
Okay, and work was 0. Say state 3, assuming the temperature in the system is 273 kelvins, what's the pressure now?
Wait, for at what state?
Right here. We didn't know what the pressure was? How could we know that? How could we even know what the pressure is?
Isn't there a relationship between pressure, temperature, and volume?
I believe that's pivot.
There's also the equality, right? Isn't there the...
Okay, so PV equals nRT. And let's see. The pressure was 1 atmosphere before.
Mm-hmm.
The volume was the same. So this is going to be constant here. The number of particles is going to be the same. Oh no, the pressure is changing.
Yeah.
The volume is the same.
Volume is... I was like, wait, don't we go less than 1 ATP?
Same. So isn't it P1 over T1 is equal to P2 over T2?
Is that right? I forget which
Boyle's
ones are...
law, Charles' law, Giemsack.
Yeah. I forget which ones are which, but that makes sense because if you divide by T, right?
Yeah, because if these are, then you divide by T.
That's your ratio.
And this constant is going to stay the same. So, and we put this and equals to the same.
Yeah. Boom.
So it's going to be the same. So I'm going to say this.
Boom.
So we want to solve for P2.
Mm-hmm. So
that's going to be P1, T2. So there's a ratio T2. So it's going to be 1 atmosphere because that's where we were here times our second temperature. Okay, all right. So this is 273 kelvins is the second one. So that's going to be
273 plus 52, right?
273. That's 0. And T1 is 273 plus 52.
Yeah.
273 plus 52 is 5 and 2 and 325.
Boom.
325 degrees Kelvin.
Yeah.
Kelvin, so
Boom.
273.
Divided by 275.
273 divided by 325. 0.84.
Boom.
So now we know that this is 0.84 atmospheres.
Yep.
We could have used Pascal's, but atmospheres rule, man. 1.
Bada boom.
Okay. Now let go of the piston. Now here we let go of the piston. And we're still in ice. Okay, so now the temperature stays the same.
But the pressure.
I'm gonna leave that alone for a minute. What's happening to the internal energy? I don't know.
So the volume is decreasing, which means the internal energy is decreasing.
Work, right? Because the volume is, so we've got negative work. We know that for sure.
Now, doesn't that also mean? Does that also mean that something else changes though, or no? Like. Yeah.
So. Right, and I put negative work here because we've got negative work.
Yeah.
So that means that the change in thermal energy was larger than the heat flow.
Yeah. Because the heat flow is 0.
Yeah. Now there are other relationships that we haven't talked about that would allow us to solve for this. And what it is, I really hesitate to even say it, is it's at the end of the chapter. Don't they have the equations at the end of the chapter? It's not efficiency. I don't think this book doesn't talk about Boltzmann. That's what I remember. I have it. Time out.
Pause. So energy.
Give me a second. I apologize.
No, yeah, you're good. I'm just re-looking at stuff.
I'm just going to write it down. Is that right?
What is the
Okay, this is the internal energy
uh-huh.
of anything, depends on how many particles and the temperature.
Uh-huh.
Okay, this 3 right here is because of the X, Y, and Z, the three
Oh, okay.
say. So it takes into consideration the motion. Okay, so we could use Pivnert from our starting point.
Find the Ed. Yeah.
We could get from the volume in STP, we could get the number of, we could get that. And so that's 3/2 in our, and then the temperature in kelvins. So we could calculate what U is for each of these.
I see. Okay.
But you know what? We're not gonna.
We're not gonna do it.
All right, so you understand why I had to find that.
Yeah.
Because it would be.
Fun stuff.
Yeah. All right, let's draw a PV diagram for this bad boy.
So we're looking at number 1. Is that right?
All right. Let's see. Pressure, volume.
PV.
And our pressures go from 1 atmosphere to 0.84 atmospheres. And our volume goes from, and here we're going to have a little problem, from 23 milliliters or cubic centimeters to 27 cubic centimeters. All right, so where should we put state 1?
What do you mean? What do you mean state
We're
1?
going to have dots
Oh, the first
on
one.
a PV diagram.
Oh,
So
I see.
The first one, that's going to be 1 atmosphere and 23. So 1 atmosphere and 23.
Up there, right?
So that's 1.
Okay, and then number 2 would be
Number 2 is 1 atmosphere, 27 milliliters.
so right there. And
1
then
atmosphere, 27 milliliters.
do we hop to number 4 or
Here.
number 3 still?
Here, the volume doesn't change,
Yeah.
but the pressure does.
So right there.
So the volume doesn't change, but the pressure does.
And lastly,
And then lastly, what do you notice here?
they're the same.
Okay. All right, so here's a PV diagram, and I'm going to connect this with this, and I'm going to connect this with this. All right, I'm going to connect this with this but I'm not going to do it yet because there's some important information.
Oh, I remember seeing. Okay, I think I saw something like this on the CSET, but it was like this. It was like.
Hold on.
Yeah.
Hold on.
Let me get over here so I can get a better
All
angle.
right, so state one, and this was for the kids to help them out doing the PV
Yeah.
diagram. And I would have shown them this before we did that. All right, so ice to hot free pit, that's process A.
So instead of
So
2,
this
it's A.
This is process A, 1 to 2. Process B, this is
B.
B, and process C, still in the ice, and the piston released. Okay, so there's 3 processes. Look. Dog lips.
Let me bring it back right there. Yeah, right there. And one more. There we go.
Include the amount of work done by the system in each step. What would be the work done by the surroundings? Okay. We're going to ignore C for now.
Okay.
But process A, work done by A, and remember work is P delta V, P delta
So it's the area
V
under the
is
curve,
work,
right?
it'd just be the area under the curve,
So for that,
and
it's
that would be
4 times.
from here to here.
So it'd be, is it 4 times point
So the pressure is,
1.6? Is that right?
pressure stays the same.
Uh-huh.
So that's 1 atmosphere times the change in volume,
Oh, I
which
see.
is 27 minus 23, 27 minus 23. That's going to be 5.
Okay, I see.
5. We're just going to call it 5 because in order to go to joules, we'd have to do meters, cubic meters, and there's 1,000,000 cubic centimeters in a cubic meter. So we'd have times 10 to the 6. Well, in fact, we could do that. That's 5 times 10 to the negative 6 joules. Not a lot of work. Okay, so this is from A. Then the work done in B,
So our
that's
pressure's
the pressure
changing.
changes, but what about the volume?
The volume does not change. Okay, that's what I thought. Because there's no area under this curve
Right.
anyways.
Yeah.
It's a line, straight
Yeah.
line. So I was thinking you had to factor in all of this.
I think you do.
Well, so if that's the case, but it's not the change in pressure, it's just whatever the pressure is.
Well, no, here's what I'm going to say. I'm going to say that it's the work done by the gas.
Oh, okay. So but that still is right. The math is still right.
Hang on, let's just check. 15.6, 15.5. Okay, no. Which sheet are on? The area. So you got a triangle. It's not giving us the answer. I will find it out for you, but I'm not going to do it now. I don't want to take the time.
Yeah, but the idea is still correct. Whatever the pressure is constant, so that's
So
the
the work
pressure.
will be the area underneath.
Yeah.
So the pressure is constant, whatever, but it's the change in volume. So that's
Yeah.
why I'm thinking here's the original volume. That's how much work, because we weren't down at 0
Yeah.
atmospheres.
What I was thinking is, area would be like length times width.
Yeah.
So I was like, from here to here is
Well,
4.
and here's what you do: you raise this axis up to right here.
Yeah.
If you raise the axis up to right here, then we don't have an
But
issue.
do you have to multiply is the pressure really the change from here to here? You know what I mean? Is the pressure really 0.16?
Remember,
It's no change in pressure. It's just the pressure.
anything times 0 is 0.
Yeah. But for A.
Well, for A, the pressure's not changing.
Right. Okay. Yeah. That's hard to remember.
We'll
Okay.
come back to that. I promise. You want to open that bad boy? Okay, so the gas is doing positive work, 5. The surroundings would be negative work,
yeah.
negative 5.
That's what I was thinking.
Okay, net work done by the system should it be positive or negative?
Well, negative plus positive, it should be, is it zero?
This question is incomplete. You mean net work? Is that the total sum of all the work?
Because if so, it would be 0, right?
It would be 0 because we ended back up at 23 milliliters.
Yeah.
So the network should be, what would you know to find the internal energy of the gas at all 3 points? You'd know the heat flow, and you'd even know the work. So there's something missing here. Use the first law of thermodynamics to find Q for each process. So this question needs to be answered here. What would he need to know in order to find the internal energy at each of the 3 points?
So we need to calculate the work for each of the 3 points, and then we need to figure out.
Well, we've got 2 unknowns.
Yeah.
We have 2 unknowns, and this is not some convenient process where we can do that. Let me just see here. Oh, that's right. I taught Boltzmann here. We're not going to do that. Okay.
This part right here?
Yeah, because I taught Boltzmann. This Boltzmann constant, that U is equal to 2/3 kT.
In order to figure out what the U is there.
Yeah.
So the idea is you solve for the U for each one using that constant, and then you'd find the work using pressure and volume.
Yeah.
And then you could find, oh, well, that's the U there. And then you'd be able to find the Q. The heat. Heat and work.
PV and KT.
Oxygen in the lungs.
Okay, here's what we would have to do. For number 1, find the number of moles. Once you got the number of moles, we can use the ideal gas law. No. We can't, because we need the internal energy. See, this leaves out that part, and I remember I had to go to other. Oh no, here it is. That's right. You have to use the root mean squared velocity. Kinetic energy is 3/2 kT. Oh. So it'll be in KE. But we need to find the internal energy. You know, it has been since 2014.
Yep.
Last time I taught this, I'm having some. There it is.
And above it, that's the one you used before, too.
So here's internal energy of an ideal monatomic gas. So we find the number of moles
And the temperature.
times the temperature, and we can get that. Okay, so, and I used to do that, and I cut that out because the explanation, it's a very good and clear explanation, but it's just too much. So we could find, if we knew the U, we could find the Q.
Yeah.
Because we can find the work.
By using the
Yeah.
pressure and the volume.
What would it mean to start in the opposite direction? Start in the ice, pull the piston out, put it in the hot water, and then back in the ice. Couldn't work backwards. It's in the ice. We pull the piston out in the ice, and then put it in the hot water.
And let it go. And
Well,
it would.
what would happen? as we put it in the hot water, the pressure would go up.
Uh-huh.
But if we pulled it out to 27 milliliters while it's in the ice, it'll be the same as holding on while the pressure goes down. So,
But that's only if we knew it would go to 27 though, right?
well, what would it mean to go? You pull the piston out. I pull it out to 27 milliliters.
Got it. We know the numbers are.
And that means that after it came into equilibrium with the water, it came up to 52 degrees Celsius. Then you could let go of the piston and
And nothing would happen. Yeah.
And then you put it back in the ice. So,
And it'll.
So is this a reversible process?
Yeah.
Should be, except for the friction. In
Yeah.
All right.
It probably won't be perfect.
Wait a minute. Okay. All right. So this was the lesson that I gave to
What-
AP.
What about this last little this last little strand here?
We're not done yet.
We're not done yet. Okay, we'll
That's
come
in
back
the
to
next-
it.
That's in the next thing.
Okay.
You want to take a break?